Dear students, today we will start with the new topic, which is pole placement and state feedback. In this lecture, we will understand that how we can design a controller for a given system using the pole placement technique or state feedback method. Now, as far as pole placement is concerned, um, because we have two kinds of approaches. One is the transfer function approach through which we do the analysis of a system, and second is the state space approach, right? So state space approach has its own advantages, and it is, limitations also. It has certain limitations also, certain advantages also over the transfer function approach. Like state variable method, basically, it needs to have the accurate system model, right? If we want to do analysis through state space, so we need to have the accurate system model, right? Because we are talking about the states of the system. We need to know the state of the system, every state of the system, right? So to have that, we need to have the accurate system model, right? Now, the advantages of state space approach or state variable method is that because the state space approach, it depends upon the state of the system. Like for any given discrete time system, the state equation can be written as fxk plus guk, and then output equation can be written as yk is equal to cxk plus duk. So in this equation, if you see, the output of the system depends upon the state of the system, and state is nothing. If we talk in a layman's statement, so state of the system is the internal description of the system. Okay, so if we do analysis of a given system through state space approach or through state variable method, so because the output, or you can say the dynamics of the system, depends upon the state of the system, so that means a state variable method gives us a representation, or you can say insight of the internal description of the system, right? Now, so when we design the controllers using state variable technique, right? So the, the most important point about this state variable technique is that we can use state variable method to design the controller for a MIMO system. It is very convenient and easy to use a state variable method to design controller for a multi-variable system or multiple input, multiple output system. If we compare this with the transfer function approach, because if we have multiple inputs and multiple outputs, so we will be having multiple transfer functions, right? But only one state space representation, and that is why this method is more convenient as compared to transfer function as far as the multivariable systems are concerned, right? So in this particular unit, in this particular chapter, we will understand, we will know that how we can design the control system or the controller for a state space model using the pole placement technique or pole assignment technique. Now, what is pole placement? So as you can make out from this word, the placement of the pole of the given system. or you can say positioning of the poles of the given system, right? This particular method is almost similar to root locus method. In root locus method, we we can design the controller using root locus method also, wherein we can have the preferred or desired locations of the closed loop poles, right? However, in pole placement technique, we can position all the closed loop poles of the system at the desired locations. However, in root locus method, only the dominant poles, right, they are placed at the desired location. Now, if we want all the poles, if we want all the closed loop poles to be placed at the desired location, right? So in that case, we need to measure all the state of the systems. We need to have the information about all the states of the system. So what is pole placement method? A pole place method is basically a method which is used to design the control system or controller so that the closed loop poles of the plant or the system can be positioned, can be located at the desired location in the S-plane as far as your continuous time system is concerned, and in Z-plane as far as the discrete time systems are concerned, right? So pole placement means the placement of poles of the system. Which type of poles? Closed loop poles, right? Now then, what is state feedback? Right? State feedback. What is state feedback? Now, if we see the block diagram representation of the given discrete time system. Okay, so discrete time system is given by xk plus 1 is equal to fxk plus guk, and output is given by yk is equal to cxk plus duk. Now if we see this, if we represent this through a block diagram, so we have a delay element, this is delay, and the output of this is xk, and input here is xk plus 1, and what we do, we feedback the state by multiplying this with a matrix f, and then we have a summing point here, and we multiply g here, and we have uk, right? And then we multiply the uk with d and xk with c, and we add them here to get the output yk. So this is the block diagram representation. Now if we see, we are feeding the state of the system back to the summing. So this is one basic thing, but however, we have some amendments, some modifications in this particular type of representation, so that we can have the desired locations of the closed loop poles of the given system, right? So now to have the, if we see, so we need to locate all the closed loop poles, okay, all the closed loop poles on the desired locations in the Z plane in case of discrete time system. Now, if we want to do this, we need to measure all the state variables of the given system. However, all the state variables of the system cannot be measured. There are various reasons behind it, right? Okay. The reason is that if we want to measure every state of the system, we need to include more sophisticated measuring instruments, right? Now, if we include more sophisticated measuring instruments, the cost will increase, right? and of course we do not have the suitable transducers which can measure all the state variables of the system, right? Now in these cases what do? We uh, you know those state variables which we cannot measure, they need to be estimated, right? We can estimate from the behavior of the system, from the behavior of the available states of the system, we can estimate rest of the states of the system which we cannot measure. Now, so what is state feedback? State feedback is a method which involves the use of state vector so that we can compute a control action, or we can develop a control law, right? So we can develop a control law for specified system dynamics, right? For a special type of system, for the specific type of dynamics of the system, we can we can develop a state vector so that we can have a control law, or you can say we have a control system or a controller for such type of system, right? Now, so this is the block diagram representation, or this is a schematic diagram of a state feedback control system. We can see here we have a reference. This is the reference, right? This is the uh, control signal, right? This is plant, this is sensor, this is output, right? And what we have an estimator. This part, this is the state estimator. This is the state estimator, and it estimates the state of the system and generate or develops a control law. Okay, develops a control law which can be used to regulate the plant within the desired limits, right? So what do we have? We have a reference, we have a control signal, we have an output, we have an estimator. This is the very important part of the system, right? Then we develop a control law for this type of system based on the output or feedback given by the estimator. Compare the controller's output with the reference, and then we have a control signal, right? Okay, so this is how the state feedback control system works. Now, how can we improve the stability of the state of a system using state feedback? Now, for any feedback system, the important aspect is that the stability of the control system, stability need to be ensured, right? So the primary function is to make the system stable of any controller. This is one of the primary functions. There are various functions or objectives of controller or control system. However, the primary function is to ensure stability, right? Now, okay, so if we want to achieve the stability through control system, okay, its stability should be assured, right? The stability should be assured, right? Now, at times our feedback while designing the feedback control system, our actual objective is to stabilize a system if it is initially unstable, or second thing is if it is initially stable, so we can improve its stability or transient response. Okay, so that means if our system is already stable, it is open loop stable, so in that case what we can do, we can improve the transient characteristics or steady state characteristics or other characteristics, frequency characteristics of the given system by designing a suitable controller, right? Now in this particular section we'll see that how we can these stability properties of the linear system can be enhanced, can be improved using state feedback, right? Now for this, let us consider a discrete model of the plant, which is given by this equation. Let us say this equation is equation number 1 here. And we have all the matrices here. F is the state matrix. This is the state matrix. This is the input matrix. This is the output matrix. Right? And xk is basically a state vector. Uk is the scalar input here. Yk is a scalar output. So this is a seesaw system, right? This is for seesaw system, right? So now the design of the controller for the plant, which is given by equation number 1, can be done in 2 steps basically. The first step is that we assume that we have all the elements of the state vector at our disposal for feedback purposes, right? That means we have all the state variables, right? That means we have assumed that we have measured all the state variables, right? The next step is that we can design a state observer which can estimate the entire state vector. Okay, so right, this is what we have to do, because if we want that all the poles of the given, all the closed loop poles of the given system are to be placed at preferred locations in Z plane. So in that case, we must have all the state variables of the system. However, it is practically not possible to measure all the state variables of the system. In that case, what we do? We design the state observer which acts as an estimator and estimates the entire state vector of the system, right? Now, in the final step, in which we combine the control law and the observer, that is the state estimator, where the control law calculations are based on the estimated state variable rather than actual state, right? So because we cannot measure all the states, so we estimate the states, and on the basis of the state estimation of the given system, we design a control law. That is, the control signal is basically based on the estimated state variables instead of the actual states, right? Okay, if we suppose that all the n state variable, let us say x1, x2, xn, can be accurately measured at all times, it is possible to implement a linear control law, and the control law is given by uk is equal to minus k xk. That is, what is this? This is the control signal. So we can have a control signal based on this particular criteria, that is minus k xk, where k is basically a matrix which contains some elements k1, k2 up to kn, right? Now the resulting, if we substitute uk, if we go to xk plus 1 is equal to fxk plus guk. So if we substitute uk here, so fxk minus g kxk here, right? So it will give me this equation, right? So we'll get this equation, this one, right? Now, if all the eigenvalues of this matrix f minus gk, if all the eigenvalues of f minus gk are actually basically the poles, closed loop poles of the system, right? So if all the eigenvalues of this particular matrix are placed inside the unit circle of the complex plane, that is Z plane, right? The state xk will decay to equilibrium state x is equal to 0 irrespective of the value of x0, that is the initial perturbations of the state. What does it mean? It means that if we can find a control law in such a way that the eigenvalues of this particular matrix can be placed within the unit circle, all the eigenvalues, that is all the closed loop poles, in that case what will happen? The state xk will decay to equilibrium, that is x is equal to 0. irrespective of what value it had initially, irrespective of the initial perturbations, irrespective of the initial disturbances, uncertainties, right? So eventually the state of the system will decay, will converge to equilibrium state. Now, what is the necessary and sufficient conditions for the arbitrary pole placement? A necessary and sufficient condition for arbitrary pole placement of closed loop eigenvalues with restrictions that complex eigenvalues occur in the conjugate pairs. That is, we can have the complex poles. However, we should have the conjugate pole pair, right? So the necessary and sufficient condition is that it should be completely controllable. The given system should be completely controllable. If it is completely controllable, only then we can design a control law uk is equal to minus kxk. If our system is not completely controllable, so we cannot have the required controller. And what is the definition of completely controllable? If all the initial states of the systems are controllable, we can say that the system is completely controllable. For this, you need to study the controllability, right? So study the controllability for this. Now, the characteristic equation here will be, right? So we have f minus gk. The characteristic equation will be zi minus f minus gk is equal to 0. This is the characteristic equation. Now, this is lattice equation number 4. Now, if we assume that the desired characteristic equation is this, which is this one, so we can get the values of A1 or we can get the values of K by matching the coefficients of these two equations, right? We have this equation, we have this equation. This is the actual closed loop equation. This is the desired closed loop equation. Then we can compare these two equations, we can get the values of K, right? Now, the calculation of the gains using this method becomes rather tedious when the order of the system is greater than 3. So for higher order system, it becomes very difficult or it becomes quite complex to use this particular approach. That is, first of all, we need to have F minus GK matrix. This matrix we need to have. Then we need to have Zi minus F minus GK. We put it equal to 0. We obtain its coefficient. We compare it with this particular equation. And then we find out the values of K1, K2, K3, K4 up till Kn. For higher order system, it is quite difficult. Not impossible, but difficult. It involves a lot of calculations, right? So what we do is we, we have a standard procedure. Okay, so we have a standard procedure. So the algebra for finding the gains become especially simple when the state variable equations are in controllable canonical form. So that means we can convert our state variable into the controllable canonical form. So in that case, it would be very easy for us to have the gains K1, K2, K3, K4, K5 like that. Okay. So how do we state regulator? Now, what is state regulator? State regulator is nothing but it's a state estimator only or state observer. So the design of state regulator is basically based on the controllable canonical state variable model of the system, which is given here. Now, from the characteristic polynomial, this is the characteristic polynomial. This is not the characteristic equation. This is the characteristic polynomial, right? So from this polynomial, we have this equation here. We can determine the values of alpha 1, alpha 2, and alpha n like that. And then we can determine a transformation matrix P that transform the system given by equation 1 into the controllable canonical form. And this matrix P is given here, where P1, P1F, and like that. Where P1 is nothing but it is 0, 0, 0 up till 1 into a matrix U inverse. And U inverse, where U matrix is the controllability matrix. This is the controllability matrix, right? This is the controllability matrix, right? Now, using the desired eigenvalues, desired closed loop poles, lambda 1, lambda 2, lambda n, write the desired characteristic polynomial. The desired characteristic polynomial is this. we have this characteristic polynomial, we have this characteristic polynomial here, and we can determine the values of alpha 1, a1, a2, a minus 1, an like that. And then we can have the matrix K, which is given by this, right? We can have a matrix K, which is given by this equation here, right? Into P. P has been obtained here, right? So we have this equation. So we need to know an, alpha n, an minus 1, alpha n minus 1 like that. Okay. So this is one approach. Okay. So we have 4 steps here, right? So we have 4 steps. The step 1 is we form the characteristic polynomial matrix here. Then we have the P matrix. Then we have the desired characteristic equation. Then we have the state feedback gain matrix K. Using this particular, this is the required state feedback gain matrix here, and then we have some other approaches also through which we can determine the state feedback gain matrix K. And one of such approach is the Ackermann's formula, and which is very convenient for computer solution. And this Ackermann's formula is given here. The state feedback gain matrix is given by this particular formula, where U is the controllability matrix and phi F is a matrix which is given here, right? So by using this particular formula, we can have the state feedback gain matrix. So in this particular lecture, we have studied about the pole placement, basic introduction about the pole placement, about the state feedback, how the state regulator is designed, what is the necessary and sufficient condition for the pole placement, right? So in our next lecture, we will be doing some numerical on this particular concept. So this is it for today's lecture, and thank you so much.